So we are live in YouTube. So
Okay.
let's for the students to post their queries in the chat box. So students will join in YouTube and then they will post the questions.
Okay.
Yeah. So you have that YouTube link now, sir?
I don't.
Okay, I will share it in Zoom. It's a Zoom chat. I'll just share, sir.
Yeah,
So,
what a Zoom link.
I-
Yeah.
I- the questions, sir.
Okay.
Yeah. Right now, 5 participants are online, sir. They are watching the event,
Yes,
but they are yet to post
yes,
their
I
questions.
can see that there are 5 people online, including me, I think. I'm also one of them.
Sir? Sir, I checked the registrations. It's 225, sir.
Okay.
Out of
Let me, so there is first query, discuss about the type of questions. Are they objective, multiple choice or subjective type? Well, the choice of questions in the exam will be multiple choice or objective type, or it could be fill in the blanks, numerical answer type. Uh, so that is the the question is there any possibilities for hands-on experiment or paying a visit to the lab? Well, it's not part of the course, but I will check with the NPTEL office if such possibilities are there. Okay, can you please explain why molybdenum is? Okay, the question is by Shobhadeep Chakravarti that can you please explain why molybdenum is beneficial for making contact in CIGS solar cells, and also please suggest some articles on CISSE solar cells. So essentially, I will answer the second question first, and then I will go to the first question. So as far as the articles are concerned, there are plenty of articles on copper indium gallium selenide solar cell, copper indium sulfur selenide solar cells. But I would recommend the book by this Handbook of Photovoltaic Science and Technology, which is a very good book which covers the detailed and in-depth information up to regarding processing, regarding junction, regarding device design, and things like that. So it's a very detailed sort of book, and I would recommend you to first read that book before you go into the details of that particular technology. So, but if you really require any, let me find out some more papers, and I will give it to my TA to post them online. So I think TAs are also there online, and they'll take care of that book. Second is, why is molybdenum necessary contact for this copper indium gallium selenide solar cell? The reason for that is, one, molybdenum makes a very good contact with the soda lime substrate. So presence of molybdenum allows a very good contact to be made. It provides excellent adhesion to the bottom substrate, and it also helps in making good quality solar cells of CIGS. So these are some reasons why we use molybdenum contact. So another important thing is that it reduces the stresses in the CIGS thin film. So mechanical stresses are reduced. As a result, films are rather stress-free, because if you don't put molybdenum, then the adhesion of CIGS film to the substrate is not very good. People have tried other metals, but they've had limited success. And this is where I think use of molybdenum has proved to be successful in case of CIGS, not in case of CDT. So because every compound is different, CDT is a different compound as compared to CIGS. They have different adhesion characteristics to the substrate. And in case of CIGS, adhesion is improved by use of and it's a sputtered molybdenum electrode. One can also make thick film of molybdenum, which can have, which is much thinner than, of course, bulk molybdenum, and it has a sheet resistance which varies from 0.1 to 0.2 ohm per square. So essentially, it's to do with the reduction in stress and via improved adhesion. It does lead to formation of molyselenide, but that doesn't seem to affect the problem. That doesn't seem to affect the device in a negative way. I hope it answers the question. But I will post more papers on CISSE solar cells that will be posted on the course portal by the TAs. So I'll do that. And would you please explain silicon ingot? So I'm not sure what exactly the question is, but basically the piece of silicon, the big piece of silicon which is made after casting, that is called as an ingot. So in case of silicon, it's mostly cylindrical piece of certain diameter. So if you just take a big casting, which is big casting made of silicon, molten silicon is then essentially molten silicon is it's casted, and this casted is this casting which is then solidified is essentially the ingot. So that's what it is. Any other question anybody has? Another question is related to how hydrogen passivation helps in improving solar cells functioning. So I believe you're asking in the context of amorphous silicon solar cells. In case of amorphous silicon, there are a lot of dangling bonds. And those dangling bonds are, when you do hydrogen treatment, the dangling bonds are passivated. Because remember, any loose bond can act as a trap, because loose bond is either it can either trap an electron or a hole depending upon the nature of the bond. So it is basically capable of trapping an electron or hole. So having hydrogen passivation allows these bonds to be passivated. Passivated meaning the bonds are satisfied. So when the bonds are satisfied, they no longer no longer trap an electron or a hole. So this is the advantage of hydrogen passivation, that is to reduce the trap density in amorphous silicon, which improves their efficiency. So the next question is, does hydrogen passivation improve the bond strength? Hydrogen passivation does not. So if I guess you're asking of silicon-silicon bonds. So if you look at silicon-silicon bond, it doesn't do anything to the silicon bond. It just forms a new bond with silicon. So whatever silicon atoms are unbonded in amorphous silicon, it goes and attaches with those unsaturated bonds. So it forms a new bond in that sense. Silicon hydrogen bond is formed, which is a new bond as compared to silicon-silicon bond or silicon oxygen bond. So in that sense, it's a different bond altogether. So somebody has asked a question on, please explain the role of back surface field in gallium arsenide solar cells. So see, generally back surface field in the device is used to reduce the surface recombination. So whether it's a silicon device or gallium device, when you use these kind of back surface field kind of approaches, they are essentially to improve the to reduce the recombination in the device. So recombination of charge carriers reduces the current density, and hence we use back surface field in the form of by putting an additional layer or some kind of device engineering to improve the. So here we use a aluminum gallium arsenide layer. Aluminum gallium arsenide layer basically creates this back surface field to reduce the surface recombination. Basically, it improves the recombination characteristics and improves the device properties. Back surface field is it's also used in silicon solar cell. I mean, it's not that it's only used in gallium arsenide solar cells. It's also used in silicon solar cell. In silicon solar cell, so in gallium arsenide solar cells, we use a layer of aluminum gallium arsenide. Whereas in case of silicon solar cells, we use typically a layer of it could be highly doped layer, which basically improves the device performance. So there are different strategies to create back surface field. But the purpose of back surface field is to reduce the surface recombination and improve the charge collection at the rear of the device. But the strategies, the same effect can be achieved in a different way in different devices. In silicon solar cells, you do the doping, and in case of gallium arsenide layer, we put a aluminum gallium arsenide back surface field layer. Of course, these two have to be optimized accordingly, but the effect The purpose remains the same, but the methodology to achieve the same purpose remains different. So if there are no more questions, we can probably close the chat box. So Murli, I think there are no more questions, so we can probably close the session now.
Yes, sir. We can close the session, sir.
Okay, so thank you, students, those who are watching in the website. If you have any more questions, you can of course always email me or ask the TAs on the platform. Okay, thank you very much. Have a great day.
I will stop the broadcast now, sir.
Okay.
Yeah. Bye, sir.